Welcome to this session on understanding and using square roots. So this is a good precursor to the quadratic formula because this quadratic formula uses square roots, and so I'm going to go over some basics that you need to know about square roots so that you can understand the quadratic formula and how to simplify things. So let's start with the definition of a square root. So we actually looked at this section 1.3. Where we referred to the symbol as a radical sign. So instead of saying square root, you'll see you're taking a rad, or it'll be called a radical. When we take a square root, we're basically undoing the squaring operation. So 3 squared gives you 9, so the square root of 9 gives you 3. It's basically going back, removing what you squared. So the actual definition of a square root is that b is the square root of a if b squared equals a. Basically what I did on the previous slide. Now, because of this definition, that means we can also get negatives as a result of a square root. So, for example, if you're squaring -3, you get 9. So the square root of 9 can also be -3 in addition to 3, because both values give you 9 when you square them. So when we evaluate, basically follow the order of operations, we're not solving, we don't have variables, we usually only assume the positive answer. So that's why we say the square root of 9 is 3. But when we're solving, so that means there's variables involved, we use both the positive and the negative answers. Now, just as a warning, when you use a calculator, the calculator only gives you the positive answer. So it's up to you. You have to make sure that you know whether you need to have both the positive and the negative answer, or just the positive answer. So I'm going to just give some examples of this. So we have the square root of 25. So when you're doing it on a calculator, you get 5. But we can also get -5 because -5 times -5 is 25. So -5 squared also gives you 25. So we have two answers, 5 and -5. So 5 squared equals 25, and in parentheses, -5 squared is 5. So both of those values give you the same answer, 25, so the square root is 5 and -5. 0, there is no such thing as like a positive or negative 0, and the square root of 0 just gives you a 0. So there is only actually one answer to the square root of 0. It's just 0. Now, negatives, if you have a negative inside the square root, if you do that on your calculator, it's going to give you error. Sometimes some people get a message that says domain error. The kind of message you get might change. When I put it in, I get a syntax error, but it's an error because we can't take the square root of a negative. So we could just say that this is not a real number. So there is no value that when you square it gives you a -49. So there is no square root. So some notation on the square roots. So we're using a here just to represent any number here. So normally we just see the square root of a or square root of number, just like square root of 4. And so that's assumed to be the positive square root. So the square root of 4 would give you 2. If there's a negative in front, then that usually means that we want the negative version. So if we have a negative in front of the square root of 4, then we want -2. So if you see square root of 4, we usually assume it's the positive one. So that would be 2. And if you see a negative in front, that would mean that it's -2. Now, there are times when we want both positive and negative square roots, and that is what you see in the quadratic formula. And so that's written plus minus. So that means we want both the positive and the negative. So that would be 2 and -2. So you get two answers when you see that plus or minus in front, the positive version and the negative version. So when you're having square roots, some square roots don't come out to whole numbers. So when you're using your calculator, you may have noticed this, that when you take a square root, for example, I have here 29, you get a really long decimal. And this is actually a decimal that goes on forever. When we're working with square roots, and I see there is, oh, don't be nervous about this. It's really not so bad, Cassandra. Don't be nervous. It's really, I hope you will see that it's not so bad. We're going to be relying on our calculator a lot, so it's not bad. So when you have square roots, and they're not, it doesn't come out to a whole number, you get a decimal. So usually in algebra, what we will do is we will keep them in the square root form so that we don't have to round the decimal and work with the decimal value. But if you have real world problems, like if you're having word problems, then we will use the decimal version. And on the assignment, I will accept the decimal version. So you can just put it into your calculator and simplify. So you don't have to worry about trying to simplify it. I'm going to show how to do that, how to keep it in the square root form, but you can use the decimal version. So there's this thing called the multiplication property of square roots. So I have an example here. If you have the square root of 4 times the square root of 9. So if you're multiplying those two square roots together, you can take the square root of both of them. So the square root of 4 is 2, and the square root of 9 is 3. So that gives us 2 times 3. And you multiply those together and you get 6. There's an alternate way to do this that actually gets you the same answer, because if you have two square roots multiplied, you can actually put those inside the same square root. So instead of writing square root of 4 to square root of 9, you could put those inside the square root so that it's the square root and then 4 times 9. So if you do that, then you're multiplying 4 times 9, which is 6, or 36, and then you take the square root and that gets you 6. So you get the same answer, you're just doing it a slightly different way, where you can combine the square roots and then take the big number and then simplify it that way. So this is what we call the multiplication property of radicals, where if you have the square root of two things multiplied, you can split them up, or you can go the other way. If you have two square roots multiplied together, you can combine them into a single square root. So this is what we use to simplify square roots. And this is what you would do if you were doing something with a quadratic formula. And it's really not as scary as it looks. It's actually not bad. So I'm going to just show you how this works. So if we want to simplify the square root of 50. So first, just as a demonstration, if you have your calculator and you put the square root of 50 on your calculator, you get a decimal. I get 7.0710678812, and then there could be many, many more decimals. So if it's not a word problem, we would not want to get the decimal version just because it's really long and nasty. So what we would do is actually simplify it. And we're going to use basically kind of split up 50 using things that we know that we can take square roots of. So I'm going to just make a little chart here. So the square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. So these are all common square roots that come out to whole numbers. And our goal is to split 50 up so that you can make it something that you can take a whole number. So you can use one of these numbers here. So I'm just writing down the most common ones. So if you know your multiplication tables, it's actually pretty simple to know your square roots, because you're just looking for like 5 times 5, 6 times 6, 7 times 7. So I have up to 8. Also, 81 is one you can take the square root of because that's 9 times 9. You can do 10 times 10, so square root of 100. So those are all square roots that come out to whole numbers. And we want to split 50 up so that we can use one of these numbers that I have listed on the left, one of these square roots. So 50 is actually equal to 25 times 2. So I rewrite 50 as 25 times 2. Now I'm going to use that multiplication property and split it up as two separate square roots. So it's the square root of 25 and the square root of 2. Now, on my calculator, or I can take the square root of 25 and actually, that's going to come out to a whole number. That's why we chose this. The square root of 25 is 5, so that's going to be 5. And then on your calculator, if you do the square root of 2, this is going to come out to a decimal. This is 1.414213562, and it's just going to keep. So it's going to be a nasty decimal. So we're going to leave it into the square root form. And we can't simplify 2. We can't split up 2 into something smaller like we did 50 to 25 times 2. So what we have here is 5 times the square root of 2. And that's what we're going to consider simplified here. It's simplified because what's inside the square root is smaller. And we kind of rewrote it so that we have a positive value in front, or a whole number value in front, to make it simple. So that is an example of how we simplify square roots using this rule about multiplication. You're trying to split it up so that you have something that's on our square root list, so that we can take the square root of something and then we have what's left over, which is a smaller number. Does that make sense? Are there any questions about that? Okay. Now there is an alternate way to do this. Instead of just splitting up as 25 times 2, but to do the prime factorization or do a factor tree, which we've done. We did the factor tree when we were reducing fractions. We did the factor tree when we were finding the greatest common factor. The factor tree gets used a lot for a lot of different things. So let's say I wanted to make a factor tree of 50. So 50, I can say, is 5 times 10. I'm going to circle my prime number, which is 5. And then 10 is 5 times 2. And I'm going to circle those prime numbers. So using the factor tree, what we could do is, instead of writing the square root of 50, we can use the prime factorization. We have 5 times 5, so we can write that as 5 squared, and then times 2. So we're just going to write that prime factorization inside our square root. And then we're doing the same thing that we did before. We're just splitting it up. And then the square root cancels out a square. That's basically what the square root does, is it undoes anything that has an exponent of 2. So if you have a square root and then a 5 squared, those cancel. And so that's how you get 5. So it's the same answer. It's just, instead of looking at it as trying to find numbers like I have on the left written here that are square roots that come out to whole numbers, you can do prime factorization and then try to take everything that has like an exponent of 2, and then you can simplify those. So you get the same answer, so you can kind of choose which method makes more sense to you. So I'm going to do another example here. We're going to do 128. So I chose 128 because it's not, like 50, it was kind of easy to say, oh, 25 times 2. 128 is not easy like that. And so in a method like this is where I would actually use the factor tree. So I'm going to start with that. So I'm going to take 128. And, well, I can divide that by 2, because it's an even number, so that gives me 2 times 64. And 2 is prime. And then I see 64. 64 we can take a square root with. So when I do this factor tree, I try to divide by the smallest number in hopes that I can find something that I can take the square root of. So 64 we can take the square root of. So I'm going to rewrite 128 as 64 times 2. Then I will split up, split it up so that I have the square root of 64 times the square root of 2. And then on your calculator, or if you look back at this previous slide, square root of 64 is equal to 8. So this will give us 8 times the square root of 2, and the square root of 2 can't be simplified. So that would be what our answer is. Now if I wanted to continue the prime factorization method, I can split 64 up as 8 times 8. And then I can split 8 as 4 times 2. 8 as 4 times 2. I can split 4 up as 2 times 2. And so I have a whole bunch of 2's here as by prime factorization. I'm just going to circle all of those. So again, I'm going to do this in a different color to show you how you can get the same answer. So we started with the square root of 128. And if I do the prime factorization method, I have to count how many 2's I have here. I have 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. So that is equal to 2 to the 7th power because we have 7 2's there. Now if we want to take the square root of something like this, the square root only cancels powers of 2. So what we could do instead is group this in pairs. So I have 2 squared, so that could be like I grouped those two together. And then I have another 2 times 2, so I can group those two together. I have another 2 times 2, grouping these two together. And I'm doing these with exponents of 2 because that cancels out the square root. And then I'm left with a single 2 left over. And so this will get me back to my 2 to the 7. So I can split each of these up. So I have 2, making sure that I have the right number of 2 squareds, square roots of 2 squareds, and I'm kind of running out of room here because of my picture, my chart. So I've just split it up, so we can split it up like I did the square root of 64 times 2, but you can also split it up multiple ways. And then each of these are the square root of 2 squared, the square root and the exponent of 2 cancel, so that's 2 times 2 times 2, and then I'm left with a square root of 2 that I can't do anything with. And if you multiply 2 times 2 times 2, that actually gives you 8. So you get 8 times the square root of 2, which is the same answer. It's a little more work this way, but you get the same answer. Do you have any questions on either method here, or just any questions in general? Is there one method that you think you like better? Like, do you prefer to do the method in blue, or do you prefer the method in red? Okay, well, I'm not getting any questions or responses, so I will continue on. Okay, example 4. So here we have simplify the square root of 29, and that was the example that I had before when I was showing that that gives you a decimal. So 29, you'd want to try to split it up to, and you're trying to split it up in numbers that you can multiply. So you don't want to do, you can't do 25 like, so we have square root of 29. While square root of 29 equals 25 plus 4, that does not mean we can do square root of 25 plus the square root of 4. It does not work that way. So you want to be careful, because that method does not work, even though we can split it up that way. We can only split it up as things that we can actually multiply together. So that's how we simplify. We have to have them multiply together. 29 is a prime number. What that means is that there are no numbers that multiply to 29 other than 1 in 29. So because 29 is prime, we can't actually do anything with it. And so we consider the square root of 29 in the simplified form because you can't split it up. There aren't any numbers that multiply to 29 that we can split this up as. So sometimes when you're simplifying, you can't actually do anything, and it's just exactly as you see it. Okay. So now I'm going to move on to things that look like things that you'll see when you do the quadratic formula. So when you have the quadratic formula, you will have things with pluses and square roots and, good question. Odd numbers are prime numbers? No. So let me go back to the previous slide. So a lot of odd numbers are prime numbers, but not every single one. You're looking for numbers that you can't divide by, like you need to kind of know your multiplication table to know, are there any numbers that I can multiply together to get to that? So I will just make a list of common prime numbers here. So we start with 2. So 2, 3, 4 is not 1, 5, 6, 7, 11, 13, 17, 19, 23, 29, 31, 37, I think 41 is another one. So the only one that's not odd is 2, but it's not every single odd number. These are numbers that if you try to divide it by other numbers, it just does not work. There's no number that you can divide into it. And there are infinite many prime numbers. So if you're not sure if a number is prime, you basically have to just keep dividing it by a number until you run out of choices. And nothing, if you can't divide it by anything, then that means it's prime. So these are special numbers that just will never have a number go into them. Does that help? Okay, perfect. So moving on to my example that looks like something you'll see when you have the quadratic formula. So when we simplify, this goes back to order of operations. You want to simplify the square root before you do anything else. In this example, the square root of 49, if you do that on your calculator, that comes out to a whole number that comes out to 7. So we can simplify this as 5 plus 7 over 6. So then we need to add the 5 plus 7, and 5 plus 7 is 12. So we get 12 over 6. And then you can do 12 over 6. You can reduce that or divide that. That gives you 2. So this simplifies to 2. So you take that square root, and then you're following the order of operations. We have to simplify on top of the fraction before we can do that division. Example 6, yes. The 7, that's from the square root of 49. So square root of 49, when you put that into your calculator, that is equal to 7. So we're just basically taking whatever that came out to be on our calculator and replacing that square root with its calculator value right there. Does that answer your question? Okay. So having your calculator handy is going to be really helpful for this stuff. So example 6, same sort of thing. We're going to simplify if possible. And so we need to start with that square root. Now if you take your calculator and you do the square root of 54, we're going to get a decimal. So square root of 54 on my calculator gets 7.348469228, and it's just going to keep going. So we could replace it with that decimal value, but it's going to be a little nasty. And so instead we're going to simplify 54, kind of using the same method that I was doing before. I'm trying to take, and I'm going to go back to my slide where I wrote all these down in. I'm trying to take this list of square roots on the left side, and I want to make sure that 54 can be divided by one of these. And I want to kind of pick the largest one. So I'm looking at the numbers under the square root, so like 64. Well, 54 does not divide by 64. 54 does not divide by 49. 54 divided by 36 is not a whole number. 54 divided by 25 is not a whole number. You're looking at each of these and you're trying to see, can I get a whole number if I'm dividing by one of these square roots? You can try 54 divided by 16, and then you get to 54 divided by 9, and that does come out to a whole number. So that's how we want to split this up. So going back, so I can simplify the square root of 54. So 54 is 9 times 3. So I can square that or simplify that as 9 times 3. And then I can split up that square root. So it's the square root of 9 times the square root of 3. I can take the square root of 9 on my calculator. That gives me 3. So this is going to be 3 times the square root of 3. So this is what I'm going to replace the square root of 54 with. So I'm going to have -5 minus 3 times the square root of 3 over 3. So I took that square root of 54, and then I have split it up and tried to simplify it, so I ended up with something that looks smaller, basically. Okay, what part are you lost on? Where did I lose you? Because the red part, where I split up 54, that's how I got to the 3 square root of 3. So where in the red part to the right did you get lost? Okay. So you get lost within 9 and 3. So 54 is 9 times 3. So I'm taking numbers that I can multiply together to get to 54. And I'm trying to pick numbers that I can take the square root of. So let me do this on the left here. Numbers that multiply to 54. So 1 times 54 gives me 54. Let's see, 54 divided by 2. 2 times 27 gives me 54. 3 times 54 divided by... Why did I write 9 times 3? And now I see why you're confused, because 3 times 18 gives me 54, not 9 times 3. Okay. Oh man, I don't know why I was just going with it. Okay, let me erase all of that. Let's keep going. So let's do 54 divided by 4. That gives me a decimal. 54 divided by 5 is a decimal. 54 divided by 6, that's the one I was looking for. 6 times 9. So I'm picking numbers, I'm looking for numbers that multiply to 54 until I get to one that has something I can take the square root of. So I can't take the square root of 1, 54, 2, or 27, 3, 18, but I can take the square root of 9 in 6 times 9. So going back to my pen and redoing this, 54 is 6 times 9, not 3 times 9, not 9 times 3, it's 6 times 9. So I'm going to split this up as the square root of 6 times the square root of 9. I can take the square root of 9, which is 3. So in this case, I put 9 in the back, so this is square root of 6 times 3. I'm going to just rewrite this as 3 times the square root of 6. We usually put the square root in back, not in the front. So I should have here minus 5 minus 3 times the square root of 6 over 3. So that was, I wrote the wrong number. Apparently I don't know my times tables today, and that would explain why you were confused. Thank you for finding that. I was just going with it. Now, one thing to be careful of is, even though I have a 3 on the top and a 3 on the bottom, I cannot cancel those out because I have to be able to also remove a 3 from the 5. So I can't just cancel out my 3's there because I can't cancel the 3 out of the 5. So that's a very, people want to cancel things out and they can't because it doesn't go out of everything there. So this would be our final answer here for simplifying, as you would just leave it just like that. And if you wanted to, you could split it up so that it was negative 5 over 3 minus 3 square root of 6 over 3. So you can actually split this up into 2 separate fractions. If you do that, then you can cancel out those 3's. So then you get negative 5 over 3 minus the square root of 6. But I don't think that's any more simpler than what I have in the purple box. I think it looks just as complicated, I guess. So I just usually leave it in the purple box form unless I can really make it simpler. Does that make sense? Okay. So hopefully on my next example, I don't make a stupid math error. So here's an example where we have the plus and the minus, because this is what you're really going to see on the quadratic formula, is you're going to see a plus and a minus. So first thing what we want to do is simplify this square root of 27. And perhaps this is where my brain was going. I was going ahead of myself. So square root of not 29, square root of 27. So when you do that on the calculator, we get 5.196152423. So because it's not a whole number, that means we want to simplify square root of 27. And so this is where actually we want 9 times 3, because 9 times 3 gives us 27. So I could rewrite 27 as 9 times 3. So then I'm going to split this up as the square root of 9 times the square root of 3. And then I can take the square root of 9, which gives me 3. So this is 3 times the square root of 3. So I'm going to then rewrite my square root here. I have 12 plus or minus 3 times the square root of 3 over 6. And I just have that plus or minus symbol there. It just kind of hangs out. So now I'm going to look at these coefficients, and I'm going to highlight these in orange. I have 12, 3, and 6. So I'm looking at those numbers. I'm ignoring the square root. I can divide all 3 of those numbers by 3. So unlike this example where I had a -5, a -3, and a 3, only 2 of those numbers could be divided by 3, not all of them. In this case, all of these numbers I can divide by 3, so I can simplify them. So the way that I do this to make sure I don't make any mistakes is I will split up this. Oops, I'm still in the highlight mode. I will split this up, so it's 12 over 6 plus or minus 3 square root of 3 over 6. And then I will reduce these fractions. So 12 divided by 6, that's 2. So we get 2 plus or minus. And then if I reduce 3 over 6, that gives me 1/2. So then I have 1/2 times the square root of 3. So I can reduce both, and I do get something that looks a little simpler. Now, what do we do with this plus or minus thing? So what do we do when we have that plus or minus? Well, we actually have 2 separate solutions here. We split it up. So we have 2 plus or minus 1/2 times the square root of 3. So I'm going to just draw an arrow. That's where we're going. And we split this up, one with the plus and one with the minus. So we have 2 plus 1/2 square root of 3 and 2 minus 1/2 square root of 3. So we get 2 answers. So when you have things with a quadratic formula, which has this plus or minus, you're always going to have 2 answers in the end because of the plus. It's saying we want the positive version of the square root and the negative version of the square root. So we have to split that up into 2 separate things to get both. Oh, wow, yeah. Once you know that's what that symbol means, it's just saying, okay, we want both. And it looks more complicated than it really is. It's just, okay, you're just writing the thing twice, one with a plus, one with a minus. So do you have any questions on this example? Okay. So that's basically, I wanted to go over this so that we led to what you would need to do for the quadratic formula so that you kind of understand how the answers in the book are coming from. But I am fine, like, on the assignment is you can just give the decimal approximation. So let's see, I'm going to just say on the next slide. So we have that 12 plus or minus the square root of 27 over 6. I am okay if you took the square root of 27 and you wrote the decimal and say you rounded it to say 1 decimal place, because the square root of 27 was 5.19. So if you round that to 1 decimal place, that'd be 5.2, because that 9 would cause us to round up. So I'm okay if you write 12 plus or minus 5.2 over 6. Then what you would do is you would split up the plus part. So you'd have 12 plus 5.2 over 6. And then you would have 12 minus 5.2 over 6. And then you would need to do the addition and subtraction on the top. So you would have 12 plus 5.2, which is 17.2 over 6. And then 12 minus 5.2, which gives you 6.8 over 6. And then you can just divide those out and round it to one decimal place. So I'd get about 2.9 as one answer. And this comes to 1.1 as another answer. So I'm okay with you doing it this way as well, and to use the decimals and to not simplify those square roots. That's completely fine. You're going to get an approximation. You won't get the exact value, but it will be close enough. Does that make sense? Okay, so do whichever method that you makes sense to you. If you do have to go on to college algebra, you will be doing this method in college algebra where you're simplifying the square root. But in the real world, you're basically doing this part instead. So it's just a matter of how far you have to go in your math so that you know what kind of math you need to know. So if this is all you need to take for your math, doing the decimals is fine. If you know you have to take college algebra, you know you have to take calculus, then you are going to want to practice using this method because you'll need that method going forward. So that's all I've got. Hopefully I didn't confuse you too much. I am so glad that you were on to correct my math. Because, you know, we all make mistakes, and clearly multiplication is something that I do wrong. So I'm glad that you're on to catch that. So otherwise I'd have to like make a message on the video or something, be like, oops, I messed up. So thank you very much for that. Tips for remembering these methods. The best thing that works for me is just a lot of practice and writing down the steps. So if you want to look into this stuff, actually these methods are covered in 8.1 and 8.2, which you don't have to read because I'm not, you know, we're not requiring you to use these methods. So if you want, you can take a look at those two sections. And then that way you could do like a few practice problems in those sections too. Those sections actually cover a lot more stuff with square roots than you guys need, which is why we don't cover them, because it covers cubed roots and fourth roots and fifth roots and things that you guys do not need to know in this class. So we don't want to confuse you more than you need to. Oh, thank you for the compliment of my eyebrows. I'm glad that I did a good job with those today. I normally have blonde hair, so my eyebrows are basically blonde and non-existent. So I have to make sure that I fill them in every time. So, any other questions? All right. Well, thank you again so much for coming. I will try to get this thing posted in the classroom probably within the next hour, so that way everybody can review it. So I hope you have a really great day. Grantham is closed tomorrow because of Martin Luther King Day. I'll probably still be checking my email though, but just if you do have to call Grantham, probably no one's going to answer. So just as an FYI, if you have tomorrow off, I hope you definitely enjoy relaxing, take some time to relax. So, all right. Well, I will hopefully see you at the next live session for week 7, and I will talk to you later. Bye.